The Institute of Microsatellite Innovation of the Chinese Academy of Sciences is one of the overall units in the field of microsatellites and related technologies in China, mainly engaged in scientific research and technological development of small satellites, micro, nano, pico satellites and related technologies in science experiments. The Satellite Innovation Institute is committed to becoming an innovation engine of China's advanced satellite science and technology, a demonstration base for the transformation and industrialization of aerospace science and technology achievements, a bridge link closely integrating politics, science, research, production and application, and an open platform for international exchanges and cooperation, serving national strategic needs and major scientific breakthroughs. It is a general research institute for communication satellites to carry out research on the overall design of communication satellites, make breakthroughs in the key technologies of high reliability and long-life autonomous controllable satellites and platforms, and improve the ability to build space infrastructure in the field of remote sensing. Set up a research institute for remote sensing satellites to carry out research on remote sensing and detection of the ground, develop low-cost, networked remote sensing detection constellations, enhance space detection, military meteorology, and marine environment remote sensing detection capabilities. As a scientific satellite research institute, it carries out space science research, and breakthrough ultra-clean, ultra-stable, and ultra-precision satellites platform, payload platform integrated design and other key technologies to improve the design capability of high-precision satellite system. For the micro-nano field, set up a micro-nano satellite general research institute to carry out spectrum-based, intelligent, and mass-produced micro-nano satellite research, breakthrough key technologies such as modular assembly of micro-nano platforms, and improve the design capabilities of high-function and low-cost satellite systems.
As the main force in the field of scientific satellites in China and the front force in the field of application satellites, it has successfully launched 75 satellites including Beidou 3 networking satellites, dark matter particle detection satellites, quantum science experiment satellites, Tiangong 2 accompanying satellites, and Taiji 1 satellites. In 2022, the world's largest and super remote sensing satellite system consisting of 16 optical satellites with 0.5 meter resolution, 4 high-end optical satellites, 4 microwave satellites, and several video hyperspectral microsatellites will be deployed. The construction is completed in Chinese hands. On December 14 last year, the Long March 3B carrier rocket successfully was launched and sent the Tianyun-2 Type 2 into space at the Xichang Satellite Launch Center. Tinlian, as the name suggests, is the information chain in the sky, so it is also vividly called the satellite of the satellite. It mainly provides data relay and measurement and control services for spacecraft, space station and mid-low orbit satellites, and provides measurement and control support for spacecraft launch. During the live broadcast, the pictures are clear and smooth and the communication is always smooth. Behind such a miracle of interaction between heaven and earth is the construction of a powerful information exchange and transmission network integrating heaven and earth by relying on the Tinlian relay satellite system. Based on the high-precision positioning technology of Beidou, the application of Beidou navigation has become more and more extensive. Not only in the field of mass consumption such as mobile phones and watches, but also in smart travel, smart ecology, and in agriculture, forestry, animal husbandry, fishing and other industries. From the positioning and navigation of mobile phone maps to takeout ordering and then to car parking, various applications of Beidou navigation have been ubiquitous in our lives.
Now the Beidou system is accelerating its integration with other new technologies. Especially the integration with strategic cutting-edge technologies such as the Internet of Everything, unmanned driving, artificial intelligence, 5G, and blockchain, which became an important enabling means for building new infrastructure.
As early as September 2009, China Starnet submitted a spectrum allocation plan to the International Telecommunication Union, short for ITU. There are 2 broadband spectrum constellation plans named GWA-59 and GW2. It plans to launch a total of 12,992 satellites. On March 7 last year, Bao Weiman, an academician of China Aerospace Science and Technology Corporation, had made it clear in an interview with reporters that we were planning and developing a space internet satellite and launched an experimental satellite. China has established a national net company, named China Xinhuang, short for GW, which is specially responsible for coordinating the planning and operation of space internet construction. In fact, no company in China has the strength to build such a huge constellation system with nearly 13,000 satellites. The establishment of China Xinhuang is a milestone in China's satellite communication and satellite application industry. The three major network operators have taken out many key staff to participate in the preparation of China Xinhuang Company. The GW constellation contains two sub-constellations. Orbit heights are also divided into two groups. The satellites of the GWA-59 sub-constellation are distributed in low orbits below 600 kilometers. The satellites of the GW2 sub-constellation are distributed in a low Earth orbit of 1,145 kilometers. The orbital inclinations of the two sets of satellites are distributed between 30 and 85 degrees. If we compare the satellite distribution and technical indicators of the GW constellation with SpaceX's Starlink, we can see that the GW constellation has many similarities with Starlink. For example, the number of satellites of the two is very staggering, and the orbital heights are divided into two groups. A group of very low orbits and a group of low Earth orbits, and the orbital inclinations are also distributed between 30 and 85 degrees. Both are satellite communication networks that can cover the world globally. According to forecasts, the low Earth orbit can only accommodate about 60,000 satellites in total. Since Starlink has currently planned 42,000 satellites, it will occupy a large number of extremely low orbits and low Earth orbits in the future. If we add the nearly 13,000 satellites planned by China this time, plus there are several other major constellation plans in the world, the Earth's low Earth orbit is almost full. China's declaration of the GW constellation plan at this time is actually competing for the Earth's low Earth orbit resources to prevent the country from facing a situation of no orbit available in the future. So this is very significant. The sooner the satellites are launched, the better. In terms of signal transmission frequency, China's GW constellation adopts the transmission frequency distribution in the two frequency bands of 37.5 to 42.57 GHz and 47.2 to 51.4 GHz. The signal frequency used by SpaceX Starlink is distributed in the relatively low frequency 12 GHz, 14 GHz, 18 GHz, around 28 to 30 GHz. Since the signal propagation loss is different in different frequency bands, it is very important to choose the appropriate signal transmission frequency. Usually in satellite signal transmission, the loss in the 0.3 to 10 GHz band and the 30 GHz band is relatively low. So we can see that the four frequencies used by Starlink are basically close to these two low-loss bands. So it can be said that the good frequency band is preemptively occupied by Starlink. The frequency bands in satellite communication from low to high are C-band, Ku-band, Ka-band, V-band and so on. The C-band was used earlier and was mostly used for satellite communications in geostationary orbits. The height of the geostationary orbit is 35,786 kilometers, which is a relatively high satellite orbit. The signal frequency of the C-band is low and the gain is also low, but the anti-interference is strong, which is more suitable for services that have strict requirements on communication quality, such as TV broadcast data transmission. The C-band is currently saturated. The Ku-band resolution is slightly higher, the gain is higher, and the antenna size requirements are relatively small, which is convenient for the use of small ground receiving equipment. It is the golden frequency band of satellite communication. The currently available frequency band resources are also relatively exhausted. Compared with the Ku-band, the Ka-band has greater rain attenuation, but the frequency is higher, and the available frequency band bandwidth is also larger, which is suitable for high-speed satellite communication. Of course, the requirements for signal receiving devices are higher. Due to the depletion of C-band and Ku-band resources, the Ka-band has developed very rapidly in the past 10 years. And the Ka-band is also widely used in the military. The frequencies occupied by SpaceX's Starlink are distributed in the two golden frequency bands, Ku and Ka. According to the radio regulations formulated by the ITU, the occupation of signal frequencies is on a first-come, first-served basis. So the good frequency band was robbed by Starlink, and China had no choice. In the past, China has suffered from the loss of frequency resources in the Beidou navigation system. Fortunately, China has applied for 4 communication frequency bands of the GW constellation in 2020. Of the 4 communication bands, 2 are in the Ka band and 2 are in the higher V band. It should be a relatively efficient frequency band that is available at present. Compared with the Ku and Ka frequency bands occupied by SpaceX, it is still a bit of a disadvantage. However, the V band, because of its higher frequency, will help to achieve higher network bandwidth. In the case of good enough signal modulation equipment and coding technology, it is theoretically possible to provide better data bandwidth than low-frequency bands. Therefore, it also depends on the future development of China's satellite technology, which is not necessarily a bad thing, though.
In this air show, various types of communication satellites such as low-orbit wideband satellites were exhibited in the public exhibition area. Such low-orbit communication satellites can solve the problem of no network signal coverage in remote areas, seas, and high altitudes. At present, China's first low-orbit broadband communication technology verification satellite has completed in the area of sensors, network weather report, satellite internet plus 5G, plus Internet of Everything, maritime joint networking and other applications. Low-orbit communication satellites often require large-scale network operation, and the demand for large numbers of satellites. At the air show, the domestic model of the smart manufacturing production line for small satellites was exhibited for the first time, which displayed to the audience the satellite mass production scene.
This production line goes from the warehousing of parts to the test line, then final finished products. Now we have complete production line control. The annual output can reach 240 small satellites.
With the continuous improvement of satellite communication capabilities, the signal receiving equipment on the ground is also being upgraded at any time. At this air show, related companies also brought the latest satellite communication equipment that can be installed on aircraft, ships and cars. High-speed network communication services can be provided no matter in high altitude, sea, or desert.
This one is mounted on the drone, this one is mounted on the helicopter. This product is what we use on civil aviation aircraft, so we have internet access on the plane.
I am now in the base of Wuhan National Aerospace Industry. This park is officially put into use in May 2021, where China's first advanced small satellite production line is located, in which annual mass production can reach 240 small satellites. We have now entered the spacecraft Smart Manufacturing Center. Behind me, these robotic arms are completing the satellite assembly. Of course, the birth of a satellite is inseparable from small parts. Then let's go to the satellite parts warehouse and take a look. The shelf seems to be as high as 5 stories. Here we can see that tens of thousands of satellite parts are displayed on these shelves. Let's ask the staff. Hi, Mr. Wang. How accurately and fast can you find the parts you need?
We use an advanced warehouse management system to achieve intelligent control of our entire warehouse, such as the code of our material and parts, as well as the name and location are all in a smart control system. For example, a communication satellite we are producing now needs to have a standalone equipment, and then the stacker will automatically send our material and part boxes out of the warehouse. Operators place our standalone equipment on top of our set of pallets. There are more than 1,800 storage spaces in our entire warehouse, which can store over tens of thousands of parts needed by our 60 satellites on the line now.
The automated guided trolley has already brought the parts needed to the production line. On this operating table, this is the satellite's module panel. At this moment we can see that the robot will put these parts on this panel. During this process, we can see that the light below has been flashing. In fact, it is taking pictures and completing the positioning. We can see it moving to a position and taking pictures. There are 6 screw holes in the panel.
移动到一个位置都会拍照。在我们舱板上一共有6个螺丝孔，看它是如何精准的对上的，它还在校对过程当中。
See how precisely it aligns. It is still in the process of adjusting. Okay, it fell perfectly into the exact spot. It would take about 4 days to assemble such a panel by hand in the past. But with the help of a robot, now it only takes a day and a half to complete.
完成这样一个舱板的装配，大概需要4天的时间。但是有了机器人的帮助，我们只需要1天半。
We have innovatively made a tight kiln coupling of this intelligent manufacturing technology in our satellite production. Improve the digitalization and intelligence of our entire production process. This in turn reduces the workload of our operators.
There's a final process to go through before the final product is certified. It is the vacuum thermal test system. This is to simulate an extreme vacuum environment. For example, the temperature of the side facing the sun under a high vacuum environment can be as high as 100 degrees Celsius, and the side facing away from the sun may be minus 100 degrees Celsius. Can small satellites operate stably and normally in this unpredictable and extreme environment? A satellite made here must pass this test. Next, it will finally usher in its new mission to be launched into space to roam freely.
With such an intelligent production line, the production efficiency of small satellites is increased by at least 40%, the production cycle of a single satellite is shortened by more than 80%, and the productivity is increased by more than 10 times. This production line realizes flexible customization to meet the production needs of different satellites. More production lines like this one will be built soon to meet the demand of 13,000 small satellites needed.
Our production line has an annual output of 120 small satellites. With a 2-shift per day, we can produce 240 small satellites a year. The satellite field of the future will be diverse. We cover communication, navigation, and remote sensing satellites, which are used for the power industry, financial industry, forestry, including navigation and aviation area.
Today, China's first batch of low-orbit broadband communication satellites has left the factory. In 11 months, Galaxy Aerospace completed this batch of satellites. The small-scale batch production capacity of the Galaxy Aerospace satellite production line was verified, exploring the low-cost development mode of our China's low-orbit broadband communication satellites. The batch of satellites has arrived in Xichang launch site and will be launched at the end of February or early March. After the successful launch, a satellite internet test network will be constructed. The delivery of this batch of satellites kicked off the low-cost batch development of Chinese satellites. Take a key step in the construction of China's satellite internet.
In the manufacturing process of launch rocket engines, more and more high-tech precision equipment have been applied, and modern 3D printing technology has also been applied to the manufacturing process of rocket engines components. The production equipment behind me is 3D printing equipment. The parts displayed on this booth are all 3D printed out. For example, the part in my hand is a rectifying grid on the igniter of a new generation of liquid oxygen kerosene rocket engine. Before using 3D printing technology, if it was done manually, it might take more than 10 days because there are more than 5,000 solder joints. 3D printing has greatly improved its production efficiency. Can you tell us what a whole process of 3D looks like?
3D printing is a digital manufacturing process. The equipment is printed layer by layer according to our predefined procedure, and finally the product is formed. Before 3D printing, we used the precision investment casting process, or so-called a ceramic shell process, for the production of this product, and it is well known that casting defects are inevitable. If the defect occurs in the blade area, the entire product will be scrapped. At that time, the pass rate of casting products was less than 30%. With adopting 3D printing technology, we now see, firstly, the production cycle is greatly shortened. What used to take 3 months to cast can now be printed in less than a week. Secondly, the pass rate has been greatly improved, reaching 80%.
technologies and intelligent equipment help the flying giant arrows, our missiles and Long March launch vehicles. The brand new production line next to me is the final pulsation assembly line for rocket engines, now being assembled as a 120-ton liquid oxygen kerosene engine. Why is it called a pulsation assembly line? It is because the products on the production line can flow according to the rhythm. Just like the beating pulse of the human body, it can flow rhythmically. In the past, the final assembly of our rocket engines used a fixed station model, that is to say, from the beginning of the assembly to the completion of the assembly of an engine, it was all carried out at a fixed station. Now our pulse assembly line is divided into 8 units. Each unit has a different job. Once the work at a unit is completed, it flows to the next unit, forming a rhythmic and stable assembly process. Large-scale automation equipment integrating various advanced technologies can be seen everywhere on this production line. For example, these machines standing in Unit 1 are the docking systems. Behind me, the 6 degree of freedom robot is gripping the turbopump of the rocket engine. The precise connection of the rocket engine turbopump and the thrust chamber can be accomplished through the integration of laser measurement technology in a 6 degree of freedom robot. In the second unit, the non-contact measurement method can replace the human eye for accurate measurement. It used to take a highly experienced assembler 1 to 2 hours to perform adjustment and measurement, and now it only takes half an hour to do the job. The third unit is the main conduit assembly. Because the workload is huge and the process is more complicated, 3 parallel workstations are set up on the assembly line. The conduits of this engine are like blood vessels in the human body. It is used to transport oxidant and fuel. These thick conduits on this engine are the main conduits of the engine. There are a total of 5 main pipes on the 120-ton liquid oxygen kerosene engine. They are like the artery of the engine. And there are dozens of thin conduits. On each engine, developers need to customize and install dozens of conduits of various sizes and shapes according to the actual state. Assembly precision is very high. The original conduit production required repeated tests and measurements on the engine, repeated misrepair and grinding, which was time-consuming and labor-intensive. Now the digital technology is on the scene, and the measured data of the engine is collected through laser measurement. Conduct virtual assembly of conduits on a measured data-driven 3D model, then followed by customized fabrication of conduits.
After changing the assembly line to an advanced mode, we put a specialized assembly team for each assembly unit. Those heavy-duty, heavy-load, low-value-added, repetitive jobs, and jobs that are greatly affected by human factors, can be replaced by these automated equipment. Various quantitative data generated in the process of engine assembly have been automatically collected and uploaded. The original handwritten and manual input method is no longer seen here. This is more conducive to the quality evaluation of the assembly quality of the engine after the completion of the engine assembly.